So we're going to be starting the next session. Amita, and I'm going to be chairing the session. Our first speaker is Alex Lev, and he's going to be talking about cleaning dirty data with Julia and Jen. So please join me in welcoming him.
Great. Okay, thank you. Hi, everyone. My name is Alex Lev. I am a graduate student at MIT in the Probabilistic Computing Project, where we work on probabilistic programming systems. And today I'm going to be talking about some work that I've been doing with a friend and colleague of mine, Monica Agrawal, on cleaning dirty datasets using Julia and a new library for probabilistic programming called Jen. So even though I'm going to be talking a lot about tabular data and how to clean it, one thing that I hope people can take away from this talk is sort of what are probabilistic programming languages and how would we put them to use, libraries in Julia, how would we put these libraries to use for practical everyday tasks? Because there's an exciting growing ecosystem of probabilistic programming libraries in Julia. There's 5 talks on them on Thursday afternoon, starting at this time as well. And so part of this talk will be about how we actually put those libraries to use. Now, I want to begin talking about cleaning dirty data with an acknowledgement, admitting that cleaning dirty data is not that hard for humans. It's annoying. It's often very tedious, but a lot of the time it's not that hard. And I realize that that's a sweeping generalization, and that depending on your data set, there are data sets that could be you can make it arbitrarily difficult to correct errors in data. But even in a data set like this, we can recognize a typo that says flays instead of false. And I would say that most of the kind of dirty data that I'm going to be talking about cleaning today is closer to correcting typos, detecting and correcting typos, than it is to solving big open math problems. And that kind of data cleaning, I think, is arguably the kind of data cleaning that when data scientists say data cleaning is our most time-consuming, least enjoyable task, this is what they're talking about. Data sets where you have numbers reported in the wrong units, where fields might be swapped, where you have typos, where you have null values indicated with lots of different possible default indicators like NA and nil and just blank, right? This is the kind of messy data that it's not what you're hiring the data analyst to do, but it takes up a huge portion of their time just to go through and clean up the data before they can do statistical analyses of it. So to make this concrete, let's look at a simple example. We can imagine that this data set came from an apartment listings website or something, and each row represents an apartment listing, and we have the state, the city name, and the rent per bedroom of the apartment in question. And just sort of eyeballing this, we can see several problems with this data set. There are obviously some fields that are missing in all 3 columns. And in the city field, there are a number of misspellings, typos, right? And as people, if you're somewhat familiar with the United States, you might be able to tell how we should fill in the missing fields and correct the typos here. So for example, in row 1, Beverly Hills, you might know, is a city in California, so we could fill in the state as California. And in row 5, Seattle is missing a T, and it's in Washington State. Right? Durham, North Carolina, which is my hometown, is spelled D-U-R-H-A-M instead of D-U-R-U-M. New York should probably be New York. And in row 3, we can't necessarily figure out what should be that middle cell, right? It could be any New York city. Any city in New York. But given that the rent per bedroom is $3,000, and given that New York City is this really populous city that has way more people than most other cities in New York, we might assume that it's a pretty good guess that that should be New York City. Humans do a pretty decent job of filling this in. But if you had 5,000 rows or 10,000 rows instead of 5 rows, you wouldn't want to sit there and manually go through and fill this in. You'd want some way to automate it. Right? And to give you a hint of where this talk is going, what Monica and I have done is we've created a little Julia library where you can take a messy data table like this. You write a very short script encoding sort of some domain knowledge about the data and the ways that it might be unclean. You pass it to a sort of cleaning function, and you get out this clean data table. But you might be thinking that this is overkill, that we followed some very simple rules, right? I said this is something that's easy for humans to do. Cleaning this data set. And it's easy in a way that some things that are easy for humans to do are hard for computers to do, like recognizing cats versus dogs, right? You need fancy neural networks to do that, even though a human can do it very quickly. But this doesn't seem like that kind of thing. This seems like something where we were pretty transparently following some pretty simple rules. And in fact, I was at a talk a couple months ago by a professor who had developed a machine learning-powered automated data cleaning system. And he had shown an example that was kind of like this one, where there were cities with typos and there were erroneous zip codes and things like that. And he was showing how his system would clean it. And in the audience, there was a famous computer scientist who had won a Turing Award, who, during the Q&A, raised his hand and asked, and I'll just paraphrase this, couldn't this be solved by some pretty simple software? And you can see where he's coming from. It feels like, if what we want to do is correct the typos in the city field and fill in the missing state values, we should be able to follow a pretty simple algorithm that says something like, if you know what the state is already, so if the state is already filled in, take a look at the city and say, check which city in that state from some knowledge base is closest in edit distance to the thing that the user typed. And just fill that in, right? And if you don't know what state you're in, look at all the cities in the United States and say which one is closest in edit distance to the thing that the user typed, and then look up what state that's in to fill in the state, right? This is a pretty simple script that you could write in not that much code. It's over here. And it seems like it would solve this problem. And I think this is what that Turing Award winner was getting at. Why do you need all of this fancy machinery to fix typos in city names? Right? And if we take our data set and we apply that algorithm, this is what we get. So it did one thing correct. It corrected Durham to the correct spelling of Durham. But there are other things here that look a little bit fishy. It's put Beverly Hills in Missouri. It's changed New York to Newark, New York. You may think that Newark is in New Jersey. And instead of Seattle, Washington, we got Seal, Alabama. Population 8,000, I think. So what went wrong here? Well, it didn't actually do anything wrong per se. There is a Beverly Hills, Missouri. It's just not the type of place where you'd expect to pay $4,000 per bedroom for your rent. And there is a Newark, New York. It has this one post office that serves all 8,000 of its residents, or it might be 4,000. And so even though it could have been Newark that the user was trying to type, we'd probably bet on it being New York, given that we're in New York State. And if we assume that our users sort of come at random from the population, there's thousands of times bigger chance that they came from New York City than from Newark, New York. Now, we could just take these kind of exceptions and do the normal sort of debugging thing of realizing that there was an error in our code and going back and trying to fix it by adding more heuristics, right? We could add tie-breaking rules like if two cities both could fit here, then we should choose the one with the bigger population. Or if two cities both could fit here, choose the one whose mean rent, according to the rest of the database, is closer to the rent in this field, right? But I think as you keep doing this debugging cycle and growing this script, that makes the script harder to maintain. It's harder to read because other people didn't go through that debugging process and don't know why you have all of these rules in there. And also, these heuristics could conflict with each other. And then what do we do? Right? If the rent tells us to do one thing and the population tells us to do another thing, how do you handle that? So luckily, this sort of problem of dealing with you're trying to reason about some unknown variables, you have some known variables, and you have a lot of domain knowledge that sort of puts those variables in context. This is exactly what probability theory is sort of cut out to help us with. And in particular, there is a formula you might have seen before. It's a theorem called Bayes' rule. It's a very important theorem from probability theory, so much so that this neon sign was built and put in HP's offices in Cambridge in England. And when a sign exists for something, it's probably because it's telling you something useful. But whereas this sign is using a logical formula, if you hit this sign, then you will hit that bridge. Bayes' rule is telling us if you have some uncertain knowledge about something, how do you update it in response to seeing some observations? So we're going to break down what this is telling us in the context of the data cleaning. problem. So there are three letters here, P, A, and B. This P is a probability distribution that's going to somehow represent all of our domain knowledge. The A represents our unknown variables, the things that we're trying to reason about how to clean and fill in. And the B represents our actual observations, so what did the user actually type? So to get more concrete, let's say we're trying to clean this row, the Beverly Hills row of our data table. Let's first figure out what our knowns and unknowns are. It may look like our knowns are the rent and the city, and our unknown is the state. But remember that we're not assuming that the user typed the city correctly. They typed Beverly Hills, but what if they actually live in Beaver Hills, Connecticut, right? We don't know. And so a more accurate picture would be to say there are kind of four variables here. There's the rent, the potentially dirty city. Then what we don't know is the clean city and the state. Now, we could try to solve a problem where we also don't trust the rent, and we also don't trust the state, right? This is a simplified version where we're assuming that the state is correct, that the rent is correct, but we don't, if it exists, the state is correct and the rent is correct, but we don't necessarily know the city. And we might want to make that kind of assumption because we know that the web form that someone used to fill this out had a drop down for the state, but a typing field for the city or something like that. There might be reasons to model it that way. So these are our knowns and unknowns, A and B, or B and A. We also have domain knowledge. So here are some English sentences informally describing the domain knowledge that we have. Things like more populous cities and states appear more often in our data set. Or per bedroom rents in a city tend to be similar across listings in that city. Right? Typed names of cities may rarely contain a typo, and even more rarely contain multiple typos. So these are the types of knowledge that we bring to the data cleaning task. And I've color-coded some things here and written how they're going to appear in the Bayes rule formula above. I don't know if you can actually see. No, they all look white. But the knowns and unknowns are supposed to be different colors. P of A is telling us things about the unknowns without reference to the observed data at all. Sometimes that's called a prior. This is our prior beliefs about which states and cities are going to show up before we've even seen what they typed or the rent, right? So that's P of A. More populous cities appear more often. The other three of these are often called in statistics and probability the likelihood. They're telling us how the observed data is more or less likely depending on the true values of the unknown variables. So we're looking, these other three pieces of domain knowledge are telling us if you knew if you knew the city, what would that tell you about the rent? If you knew the real city name, what would that tell you about the typed city name? Right? This is P of B given A. P of the observed, the probability distribution over the observed variables given the unobserved variables. So once we have those ingredients, we can actually use this formula. What this formula tells us to do is it tells us how to compute this number P of A given B. So A are our unknown variables. If we plug in a particular hypothesis, like Beverly Hills, California, or Beverly Hills, Missouri, as A, and we plug in our actual observed values as B, then it tells us how to compute P of A given B, the probability of A being that hypothesis, given that B was these observed values. Right? And so the higher that number, the better that hypothesis. Right? And so we're just going to plug in P of B given A times P of A over P of B. But notice that no matter what we plug in for A, Beverly Hills, California, or Beverly Hills, Missouri, the denominator of that fraction doesn't depend on A at all. Right? It's just P of B. So that's going to be constant no matter what hypothesis we're trying out. So we really just have to compare the numerators of our different hypotheses and see which ones are bigger. And so we're just going to do that. We're going to check for each of the hypotheses, Beverly Hills, California, and Beverly Hills, Missouri, which gives us a bigger number. This piece, the piece highlighted in green over there, is our prior knowledge, and that's telling us to compare the populations. Remember that P of A was about more populous cities appearing more often. So this P of A number is going to be somehow related to the populations of each city. And because Beverly Hills, California has more people than Beverly Hills, Missouri, that factor of this product of two factors is going to be weighing us in favor of Beverly Hills, California. But not a ton, because Beverly Hills, California is not a hugely populous city either. Right? Then this other piece is telling us to weigh, okay, well, it's actually two things. how likely is Beverly Hills to be typed if what they meant was Beverly Hills? And this is the same in both hypotheses. In both hypotheses, there are no typos, right? And then the other piece is if they were in Beverly Hills, California, how likely is $4,000 rent versus if they were in Beverly Hills, Missouri, how likely is $4,000 rent? And that's going to be the real deciding factor in this example. Now, I know I haven't been precise about how we actually assign numbers to this, but you can sort of see how if we can be precise about how to assign numbers to this sort of weighing of the products and stuff like that tells us how to trade off between these different, what were before heuristics, and to do it in a principled way. So this is going to let us say that overall, California is the better hypothesis and to choose it. And this observation that cleaning data can sort of be thought of as a probabilistic process is not new. It was, or it appeared relatively recently in the literature, but it's not mine. It's this paper called A Formal Framework for Probabilistic Unclean Databases. Our goal, what Monica and I set out to do, was to create a general purpose data cleaning system. So how do we actually make this observation that probabilities are useful practical, right? So we wanted to create a general purpose system where users could encode their domain knowledge into a little script. And once they had done that, they could feed in this messy data table and have cleaning happen automatically. And we're not trying to completely automate the process of cleaning. There's still scripting involved. But instead of heuristic imperative scripts, like we had before, we now have declarative probabilistic scripts. Okay? And there's a reason to think that this kind of declarative probabilistic scripting, where people are actually writing code that says what they assume about the data and the ways it might be unclean, there are reasons to think that's a good idea. Personally, I think that it makes your code sort of more legible and maintainable if we can pull it off. But beyond that, like looking in the wild, if you look at organizations that have big data cleaning needs, like the Department of Energy, they have like slide decks that you can look up that are training people on how to clean messy data. And they don't say, here's what to do for each row. What they say is, here's what you might see when you look at the data, right? So when they say something like, unit conversion errors might be possible, you might see therms of natural gas instead of million cubic feet. What they're telling you is, what you should expect to see is this number in million cubic feet, and it should make sense as a number in million cubic feet, but you might see, with some small probability, people putting it in therms of natural gas instead. They don't tell you how to convert between them. It's kind of implicit that if this is the model of how things get messy, you should know that in order to clean it, you have to recognize when something is probably in the wrong unit, and then convert it back to the right unit, right? Of course, this is much easier said than done, to create a scripting language where you can encode arbitrary domain knowledge. And this is like one of the two main challenges. The two main challenges are, how do you actually have a formal and flexible way of letting people encode that domain knowledge? And two, once you have them writing this domain knowledge in a script, how do you actually do the cleaning? And this is where the probabilistic programming stuff comes in. Probabilistic programming systems are designed to make probabilistic modeling and inference more accessible and easier to use. They provide two fundamental features. One is modeling languages for expressing probability distributions, very complex probability distributions, by writing things that look like programs. We'll talk about that in a minute. And the other is, once you've expressed your probability distribution, they can automate the approximate application of Bayes' rule to do inference in these probability distributions. There are a lot of probabilistic programming languages out there. If you've heard of something like Stan or Pyro, these are systems, especially Stan, is a system that is really for sort of a special purpose use. It is designed to do the kind of computational statistics models that statisticians do, and it's very popular for that. But it's kind of restricted in that you can't express arbitrary models like things about California and Beverly Hills. Pyro is not specialized in terms of the models that it can represent, but it specializes in using neural networks for inference. So it's going to help you train neural networks to approximately solve this inference problem that you've specified in your model. Julia has a few different systems, including Turing and Gen, and these are what's known as universal probabilistic programming languages, sometimes called Turing-complete probabilistic programming languages. And these are languages in which you can express any probability distribution that's computable. And we used Gen here, which is a language that also has something called programmable inference, which is going to let us circumvent its inference engine and customize the inference engine in order to be better suited to the problem that we're trying to solve. So how does this actually work? What do I mean when I say they let you express any probability distribution? So remember that our goal is to have this distribution P, this domain knowledge about variables A and B expressed somehow, right? Now, mathematically, that means that we're specifying probability distributions. So this P of A thing is actually a distribution over all possible values of the unknown variables, telling us which states and cities are going to be more likely and which states and cities are going to be less likely. Right? So it's a probability distribution. And P of B given A is a set of probability distributions. For every A, so if A is Beverly Hills, California, P of B given A is a probability distribution over rents and typed names. So Beverly Hills 4000 is a pretty likely B, given A equals Beverly Hills, California, whereas Durham 800 is a very unlikely B, given that A is Beverly Hills, California, right? And probability theory tells us that specifying these two things separately is the same as just specifying one big probability distribution over all four of the variables, or, the A and the B. So we just need to say what combinations of rent, dirty city, clean city, and state are likely, and which combinations are unlikely. So we need some way of expressing that, and that's what Jen is going to have to give us. Sorry, I meant to click that. So that's P of A comma B is how it's written, the joint distribution on both of the sets of variables. So what probabilistic programming languages do is they recognize that if you write a simulator, so a program that simulates fake data sets, okay, you've kind of specified implicitly a distribution over the variables that you're simulating. Because to know whether a state and a city and a typed city and a rent are likely, we can look at the program and ask, is this program likely to have generated those values? And to know if they're unlikely, we can look at the program and ask, is this program unlikely to have generated these values? And what these probabilistic programming libraries do is they let you write that simulator code using a couple well-placed macros, in Julia's case, to help it sort of annotate where the random choices are happening, and turn that code from a simulator into all sorts of useful auxiliary pieces of code that do things like compute probabilities. Okay? So what this looks like in practice is that you can use this for all sorts of things. Data cleaning is not a use case that you'll see if you look at probabilistic programming systems. It's a kind of atypical use case. But for example, in Gen, you can use it for computer vision by writing a simulator that randomly chooses a body pose for some human mesh model, right? So it randomly simulates some joint angles, and then passes it through OpenGL and actually gives you like a depth image out, a noisy depth image out. And then you can ask it, given this depth image, what were likely body poses. Okay? Similarly, for us, we're going to have a simulator that simulates clean data and the dirty data, right? That simulates the clean data and makes it dirty. And we're going to be able to use inference, this red arrow here, to sort of go from the observed values and kind of invert the simulator probabilistically. Okay, so what does this actually look like in Gen? So here's some Gen code. I'm not going to go into a ton of detail here, but @gen is a macro which says this function that I'm writing is a simulator that I want you to treat as a probability distribution, as inducing a probability distribution. We're then going to write our rent model, and its goal is going to be to sample all four variables that we're interested in, and to do so in accordance with our domain knowledge, which is down here in green. This is the knowledge that we had wanted to encode. So in order to encode the fact that more populous states and cities appear more often, we are going to sample a state and a city, that's on lines 1 and 2 here. We're going to sample a state and a city proportionally to their populations. So this is currently assuming that we have, from the government, you can download a list of populations of every city and state. We'll look at how to relax that assumption in a moment. So this is just choosing proportionally states and we pass in the populations, and it will choose a state proportionally to the populations. But you'll notice that there's some other stuff there. There's that @trace macro. That tells Gen, I'm adding a random variable to this distribution. And I want it to be called state, which is the symbol at the end of that @trace invocation. And then the city, we're going to choose proportionally and add it as a random variable called city. And then we're going to sample a dirty city by randomly adding typos. So this add typos function is going to flip coins with 10% probability. It's going to add a typo. randomly by choosing a random substitution, etc., right? A substitution, insertion, or deletion. And it'll keep flipping coins with 90% probability of tails until it gets a tails, at which point it's done. So with 90% probability, it doesn't add any typos at all. With 10% probability, it is continuing to add typos, right? And then rent, and that's how we encode that more and more typos are rarer and rarer, but that they can occur. And the rent, we're going to, again, assume here, we'll relax this in a minute, we're going to assume that we have the rents downloaded from the government, the mean rents in every city. Okay? And we're going to do a draw from a normal distribution, so like a bell curve around that mean rent to simulate the rent value for this thing. And then in Gen, we can do inference by specifying our observations by creating this thing called a choice map, which is kind of like a dictionary mapping variable names to their observed values. But we only map the things that we've actually observed to observed values, and then we ask Gen to fill in the rest using one of its inference algorithms. Okay? So the first thing that Monica and I did was build a slightly cleaner syntax for expressing these kind of models when they are actually for tabular data that might be clean and dirty. And so the syntax is a little bit cleaner, and since we actually have the names of the fields as strings right there in the model, you don't need to set up your observations yourself. We can just automatically pass in a data table to this clean function, and it will match up all of the clean and dirty values to the right variables in the underlying Gen model. But this is kind of just plumbing. We haven't really done anything that interesting. I think it's still useful plumbing, but this is really just a thin layer on top of Gen. So the other thing that we do is we say, okay, see all of these things that we just assumed you knew, the state populations, the city populations, the mean rents, and the standard deviation of rents. We're going to allow you to replace those with underscores, meaning learn these parameters from the rest of the table. So it's going to use an expectation maximization algorithm to go back and forth between trying to clean the data and based on the hypothesized clean data, estimate those parameters. And then based on the new estimated parameters, go back and re-clean the data. And then so on and so forth for several iterations. And the fact that we were able to do that in Gen is because of Gen's programmable inference, which lets you write sort of custom inference algorithms to extend the ones that it provides. So we have some very preliminary results showing that if you write your models to encode the same knowledge encoded by other systems, then you can recover the performance of those other systems or sometimes do better on certain tasks. And this was all made possible by Gen. There's a lightning talk in that session on Thursday on Gen that I encourage you to come to if you're curious. And that's it. Thanks.
Any questions?
Is there underlying assumption of kind of missingness? Isn't the data missing at random, non-random, etc.?
Yeah, that's a great question. So right now the answer is yes. We are assuming that the missingness of data, like there's no way to model the missingness in our current system. So you can't say that, you can say that data might have typos, and you can even make those typos more or less likely depending on other factors and stuff like that. What we'd like to be able to do eventually is to say, you can say that the data is more or less likely to be missing based on other variables that you've already sampled, right? So that you might want to say that, data from certain neighborhoods is more likely to be missing or something like that. And that means that it's going to bias you during inference toward thinking that a missing value is more likely to have come from one of those places, that missing data is more likely. And we have ideas for how to extend it to.
Okay, and if possible, kind of general ask. I started looking at Gen and got very excited. But then I noticed, okay, there are like 3 other or 4 other PPLs just in Julia, right, and Spira. Spira tutorial looked almost exactly like Gen with a fully dynamic DSL, the same trace and stuff. So is there some way to make it have like a matrix in one of those other meetings, so like the differences would be explained?
Yeah.
Otherwise, it's really kind of a little bit annoying.
Yeah, that's a good, I think that it's getting to the point where there are so many probabilistic programming systems that someone really does need to go and write a clear explanation of the differences. I'm not sure if anyone knows enough about all of them right now to do that. And I'm sure that my attempts would be biased towards the ones that I know more about. But I would say the modeling language is often not where to look for the differences, because a lot of these languages have similar modeling languages. So the real thing is how does the inference work? What are the assumptions that are made by the inference engine? What kinds of models does the inference engine work well for? What kind of customization can you do? How easy is it to extend? Yeah. That's probably too strong a statement. I'm sure that there are interesting differences in modeling languages, but.
So you say like if I don't know the probability and you provide underscore. So if I want to provide a prior on a parameter, like can I do it in Gen?
Yeah. So in Gen, the answer is yes. So in Gen, you can express models that essentially, so those underscores are not actually a feature of Gen, right? Gen doesn't have you place underscores for parameters. In Gen, there are multiple ways to handle those parameters, such as putting priors on them, or using gradient descent to find maximum likelihood values of those parameters and things like that. For this system, we didn't want to let people place arbitrary priors on those parameters because a goal of this system is to be usable by people who want to do data cleaning without too many pitfalls. Now, if you can place arbitrary prior distributions, you can make inference much harder. And this is one of the problems with probabilistic programming languages, is that you kind of have to code your way around the holes in the inference algorithms. You have to make sure that your models are actually going to lead to tractable inference. And so this language is trying to be restricted enough, that this p-clean language is trying to be restricted enough that we can ensure efficient implementations of the EM algorithm that underlies it.
So the add typo in is the build the function that you provide.
Yeah, it's implemented in Julia, and it has some custom inference logic as well. So this is something that Gen is going to let us do as well. It lets you take arbitrary pieces of a model, which we can then provide as a library for the data cleaning use case, and attach custom inference logic to those pieces of a model.
And can I provide a customized distribution?
Yes,
like,
yes, you can write your own distributions, absolutely, yeah.
And where do you get the distribution? Like for the normal distribution, where do you get that distribution from the distribution package?
So Gen has implementations of a bunch of distributions, but I think that for many of the distributions, Gen uses distributions.jl.
Okay.
But it has its own distribution interface that you have to satisfy.
Okay, thank you.
Mm-hmm. Thanks.
So let's thank Alex one more time.